Welcome to Lecture Online. In this video, we're going to find the center of gravity of a semicircle. Notice the center of the circle is at the origin. Of course, if this was a complete circle, it would be at the origin. And we realize that the center of the gravity will be somewhere on the y-axis, which means that the x-coordinate in this case will be 0. Now the y-coordinate, we'll go ahead and find that. So we'll use the equation right here. And what we need is a small little area element. So this is my small little dA. My dA is equal to the height, which would be y, times the width, which would be a small little dx. So this would be a small little dx for the width and y for the height. And the center of gravity, that small little slice, is right there in the middle, which means that my y-coordinate of the center of gravity of that small little slice is equal to the full height, which is y, divided by 2. We can go ahead and plug that into our equation right here. So we get the y-coordinate of the center of gravity is equal to the integral of and this is where I'm coming from, right there. So that would be the center of gravity of the small little segment, which is y divided by 2, times the dA, which is y times dx. And we have to take the whole thing and divide it by the area of a semicircle. The area of a semicircle would be equal to 1/2 pi r squared, right? Pi r squared is equal to the full circle area, so we take half of that. Now notice that we can factor out a 1/2 in the numerator. We have a 1/2 in the denominator. They'll cancel out like that. So now we have the y-coordinate of the center of gravity is equal to the integral of y squared times dx divided by pi r squared. Now, of course, since we have a y and an x in the integral like that, we have to convert y to an x. The equation for the circle is equal to y squared plus, I probably want to start with x squared, right? So x squared plus y squared is equal to r squared. That's a standard equation. So we can say that y squared can be written as r squared minus x squared and substitute that into our integral right here. So we get the following. This is equal to the integral of r squared minus x squared times dx divided by pi r squared. Of course, the integral is going to go from minus r to plus r, or I can take it twice going from 0 to r. So I can multiply this times 2 and integrate from 0 to r instead of just integrating from negative r to r. I always like to have a 0 in the limits if possible. All right, let's integrate this. So this is equal to 2 times, that would be r squared x, this is squared, r squared x minus x cubed over 3. The limits are from 0 to r, and divide the whole thing by pi r squared. If we now plug in the limits, we plug in the upper limit, we get 2 times, that would be r squared times r, which is r cubed, minus r cubed divided by 3. And when we plug in the lower limit, we get 0, so we don't need to do that, divided by pi r squared. So this is equal to 2 times r cubed minus a third r cubed, which is 2/3 r cubed. Divide the whole thing by pi r squared, and then this r squared comes out 2 of those. We put the 3 on the bottom, we have 4 on the top, so this becomes 4r divided by 3 times pi. And notice that is the exact same result as we got when we did a quarter circle, which makes sense because if we find the y-coordinate of the center of gravity for the right side, and we find the y-coordinate for the center of gravity of the left side, it would make sense that when we add them together, we get the exact same y-coordinate for the whole semicircle, which is what we just got. So in this case, the x and y-coordinate of the center of gravity is equal to 0, because 0 is the x-coordinate for the semicircle, and for the y-coordinate is still 4r divided by 3 pi, just like it is for the quarter circle. And that's how we find the center of gravity of a semicircle.